Hey everybody, my name is Tim. Welcome back to the channel and welcome to Vellum Fundamentals week 2. The content of this week has changed a little bit based on the suggestions that I got, which was kind of the goal of, like I mentioned last week. Like I kind of want to make this a thing where I get asked questions and I aim the content at the questions that I get. And I got some questions about stuff like the different constraint groups, how to work with those. So we're really going to dive deep into that. We're going to cover actually some stuff that's already getting a little bit more advanced. And I was contemplating if it was going to be too difficult for a week 2, but I'm trying to explain it as easy as possible. And if it's too difficult, you can always come back to this. But it's gonna have a lot of interesting stuff like sourcing stuff into Vellum, making sure that it doesn't source into other objects, sourcing at different pscales, making sure the constraints sort of match the scale of the stuff that you're sourcing, having stuff inflate over time, being able to use Vex to manipulate that. We're going to dive a little bit in some SOP solver magic. It's going to be very exciting. We're going to make the 2 examples that you saw in the intro. So if you want to get the source files to everything discussed in this week's video, including sort of the final renders that you saw in the intro, so the entire setup for that is going to be in here as well. You can get it on Patreon or on Gumroad. Aside from you getting the file, it also helps me out with the just with the channel, so I can take some time off work to make videos like this. So if you're interested in that, get it over there. Helps me out, helps you out. We both help each other out. And without further ado, let's actually get into the video. All right, so we've got a lot to cover this week. So we're going to be making both this one and we're going to be making this one. So they're kind of all both focused around emitting stuff into a Vellum simulation, which is something that's quite interesting to do, and also manipulating constraints. Like last week, we talked about these constraints, right? The different constraint types, like the bend constraint, distance constraints, something for like to setting up pressure with the balloon. You can actually iterate on these constraints individually to get some stuff done. And that's like, I got some questions around that. And I thought, because initially I had thought to make a different topic for this week. I kind of first wanted to mostly focus on like soft bodies and remake sort of the Vellum booty shake, like I mentioned. But actually I think maybe covering sort of these constraints and how we can sort of individually manipulate these in solvers might be more interesting. So yeah, I have these 2 setups here. So here we have papers falling, as you can see, and you can see they're actually being emitted at different scales. So that's a thing that we're going to be covering. That's actually a little bit more advanced already, but something that you cannot do natively, and we need to actually do some manipulation of constraints. So that's going to be interesting. And then here's one where you can see we're sort of emitting bubbles in there. It's being blocked out by the text that we have here. So 2 quite interesting sort of examples, and these are things that you would really probably use in production. This is really a really typical Vellum use case. Again, these might be a little bit more on the complicated side, but I'll talk you through it. And first, we're going to do some just regular examples of how we can do these things. So I hope you've been playing around with just with Vellum in general after last week's lesson, and you're up for some more good stuff. Right, so I'm going to make a subnet here. If you didn't know that, you can make subnetworks in Houdini, and those are sort of containers for other nodes. Like you can have camera, and you can see here I have a lob network here for rendering, and geometry nodes are just nice for organizing. So let's call this examples from the live class, or not necessarily the live class, but pre-recorded live class. But yeah, we're in here. We're gonna make some examples. So let's just do another geometry node. Let's make a sphere. Let's make a polygon. And let's make a balloon. All right. Now let's do a solver. Let's attach it to the correct one. All right, and we have it falling down. We don't want that. Let's turn off the gravity. And then we don't have anything going on. And again, just to reiterate, we can also build our own Vellum solver, making a dot network. Doing a Vellum solver. Vellum object. We put and then not in that Vellum source, we put the Vellum sort of the thing that we want to source in the Vellum source. We can do that by either sort of copying one of these paths in here, or if we just connect it like this, we can do pop input input path, open bracket, 2 dots, and then first input, and then another backtick. You can see it appears. Then we can do it on the constraint path as well, and then we grab the constraints, and we essentially got the same thing. We can actually also solve that way. So 2 different ways of doing it. I like to use this one a lot when I'm doing sort of more custom setups, and this one is easier if you just want to drop something down and just test it out. Like kind of, I call it a drop test, where you're like just dropping something in, see if it works. So depending on what you're going to be doing, you're either going to be using this one or this one. Yeah, this is just a wrapper for this. If you go in here, it's essentially we're just inside of of the same type of dot network. So last week also we've discussed sort of these different groups that are in here. So let's have a look at our constraints. Let's hide our attributes, and we can actually only show the group attributes. And you can see we have a group bend and we have a group stretch. And we can make another group as well. So bend and stretch are mostly coming from here, from the cloth constraint. And again, how that worked, like I explained, like if you want to reiterate, like I'm going to reiterate some of this, but like watch last week's video if you want to get a little bit more into depth or on some of this stuff. But again, we have these cloth constraints, which sort of these constraints are sort of containing sort of we have this. So we have the geometry here, which has some information on the points, like the mass and the drag and stuff like that. How big are the points? You have the constraints, and those are sort of these have a length, and they're sort of and they have an attribute on it that says how much they can bend. So and they have essentially these attributes that are gonna be saying, all right, how much can I stretch, and sort of based on the stiffness, or how much can I bend. So they both have, like, there's distance and there's bend, and like how much can I bend, how much can I stretch. And then we have the pressure constraint, which we can enable the group in here and just call it a different name. I like to call it pressure. I'm not sure why it's not just by default as a more logical name, but we can have a look at the pressure constraint, delete non-selected. You can see this is just one single primitive that sort of goes all across our sphere, and then that's being measured. So how long is that thing? And that essentially constrains the pressure of our balloon. So if the rest length of this thing becomes bigger, essentially that's gonna say, all right, the pressure on our geometry is gonna go up. All right. So the sort of the pressure on this thing is gonna go up. So essentially the volume is gonna increase, and then we're gonna have the balloon inflate. So we can try that out. If we increase the rest length scale here, you can see it inflates. Or if you make it shorter, you can sort of deflate and be all weird. But essentially, sort of just the pressure that's pressing on these other constraints. So they're stacked like that. And right now, like in previous lesson, we've only sort of discussed how we can sort of set parameters in here. We can also do this dynamically in the solver. So we can also do is we can, for example, let's just do it in this one. You can go in here. You have a thing called Vellum constraint properties, and we can just put it in here. Let's put it in here, and here you have different things, like for example, rest length scale. So this will scale from it will scale the original rest length. So if I put 5 in here, it's gonna completely break. We've discussed this last week as well. It's because now it's scaling the rest length of all these constraints. And like I mentioned, it's also gonna scale the pressure it's gonna scale the pressure constraint, it's gonna scale the bend constraint, it's gonna it's gonna increase sort of the scale on all of these things. But we probably only want to do this on the pressure. So let's say if we do this just on the pressure, then we get kind of the same thing that we got sort of in here, right? So because now we're just doing it on the pressure constraint. Like if we, for example, we could do pressure and stretch. We could do pressure and bend. You have control here over just the type of constraints that you wanna iterate on. And you cannot just do this in these Vellum constraint properties. You could also do this in a wrangle or in a subsolver. So I could say, for example, geo wrangle. So this might already get maybe a little bit complicated for some of you. We're gonna use a little bit of Vex. I'm gonna talk you through some of the Vex. You know what? Maybe let's do it first in a subsolver, and then we're gonna do it in with some Vex. There's multiple ways that you can sort of manipulate these constraints. So if you don't know what a subsolver is, I actually have a dedicated course to this. There's a couple of chapters on my YouTube channel. It's about building custom solvers, and we actually learn how to build a particle solver completely from scratch, just manually yourself. So not the way that Houdini does it. You actually script it, you actually code it yourself, which uses subsolver. But subsolver is actually just a way that you can sort of iterate on geometry just over each frame. So this will look at the previous frame and then does something on it. Then if we go in here, we can see this will go over this geometry. But as we know, our constraints are another input. So this does not make any sense for us to do it like this, because we need this to run on our constraint geometry. Now you kind of need to understand sort of how DOPs work. There's kind of if you just select something here in DOPs, you can see here in your geometry spreadsheet, like it looks a little bit different. And you can actually see here we have our Vellum object, and what do we have inside our Vellum object? There's like a couple of different groups. The main things that are interesting right now is we have here the geometry, and we have constraint geometry, and there's also collision geometry, patch geometry, a whole bunch of stuff. We're going to mainly be focusing on these two for now. And there's also a group called forces, like if you have gravity. So it's essentially just a drop-down menu of all of the stuff that's in your in your DOP network. Your geometry is going to be just a geometry, so from the first input, and the constraint geometry is going to be the thing from the second input, so our constraint. And we can actually tell this subsolver, all right, where do you want to run on? So here you can say data name. That's the data that's coming from here. It's currently running on geometry. If we type constraint geometry, can go in here. And right, there we go. You can see now we have our constraints in here. So now we can do stuff with just regular sub stuff inside of our solver. So you can do a whole bunch of cool things. Again, check out my custom solvers in Houdini if you really want to go in depth with that, but we're going to be using it here as well. So what we can actually do is we can make a wrangle, for example, and we can say we're going to run this over primitives, because these are primitives, and we're going to run this over pressure, similar to what you do with the other thing. And then we can say that we want to do something similar to what was happening here. So this is increasing the rest length scale. So let's say we want to increase this over time. So let's say that we want to say, right, if you put an add symbol, you're going to say, all right, I want to use an attribute. Attribute, easy. So add rest length. And we're going to say, right, and this is going to run every frame, by the way. So let's say we do times equals, it means we're going to do it times something, and we're going to do this every frame. Let's say we do it a little bit every frame. So times 1.05. So it's going to increase 5% every frame. And let's have a look at this. All right, so let's play. You can see now it's gonna increase 5% every frame. You can see it sort of also spinning around because it's sort of getting a little bit crazy. This is just by increasing this pressure constraint. So we have sort of manual control over sort of how we wanna increase this. We can also put limiters in here if we want this. And guys, so like if you don't know Vex, I guess this is also going to be a sort of a beginner Vex course. We're just I'm going to talk you through every single step. So like I'm going to try to make it as easy as possible. But if we look at these attributes, let's just hide everything. And I mentioned this last week as well. So we have rest length and we have rest length oric. So the original rest length. You can see our rest length is actually increasing. And we just need just want to do it from our pressure constraint. You can see our rest length here from our pressure constraint is increasing. The rest length origin is remaining the same. So let's say, all right, but let's do an if statement. If statement is pretty easy. Like if you want to know how you can do this stuff, if you type if, open bracket, you can actually middle mouse over the, no, not middle mouse, you can hover over it and press F1 and it will open up Houdini help. And then you're going to see that apparently it doesn't do it with if statements. Normally on everything you type, it will open up help function, I guess for this one. For some reason not, all right? Gotta love recording. All right, anyway, if, we're going to give it a statement. So let's say that if, let's do a simple one first. Let's say, all right, at frame. So if the frame is below 30, close bracket, and then you can put a statement after this. You can do it two ways. You can put statement like this, so after it, and we'll just run it. Or I can, and we can try this out. All right, let's reset our simulation real quick. Right, you can see now it was just, it's going to inflate until it hits frame 30 and then it's going to stop. So you can do it like that. Or if you want to put multiple statements here, for example, you can do sort of this is curly bracket thing. I think that's what you call it. And then you can just put it in here, just with an indent, just press tab and then whatever. And then it's going to do the same. So you can, again, run it like that. So we can put multiple types of sort of comments in here, right? All right, maybe what we don't do instead, let's not do the frame. Let's say that, all right, if the rest length is below, and we're going to open bracket, close bracket. So if you remember from order of operations, mathematics, if you put something between brackets, it's going to execute first, right? So you want to say, all right, rest length oric, so original rest length times 1000. So we want to only increase it 1000 times. So now it's going to say, right, if the rest length is below the original rest length times 1000, it's going to inflate, and after that it's going to stop. So let's have a look. Keep inflating, keep inflating, keep inflating, and it stops. And again, you can combine this with different types of comments here. If you put, for example, because you can actually combine this with like other statements as well. So if we type, for example, so you want to make a second statement, you could, for example, say, right, two ampersands, and then say, right, at frame is below 50. So now it's going to check, right, if the rest length origin is below 1000 and the frame is below 50. So now we're going to say, right, either which needs to be true. So it's going to increase and it's going to stop at frame 50. Or let's say we had this at like frame 5000. So it's going to essentially say, right, both need to be true. Right, so here, main thing I want to learn about Vellum is how groups work inside the solver, such a pain to figure that stuff out. So there's this is something I want to cover. There were some other questions as well. I got some questions on Patreon, which I actually made a HIP file for. Like, if you have questions about stuff, you can always ask me on Patreon, on Discord. I generally like to help out. So like, I actually have an interesting sort of example that I'm going to cover in a later video about sort of cutting strings, which is also going to be interesting because it took some time for me to figure out, actually. And like to break them sort of not based on pressure, but you actually just cut them. So that was interesting. Here's a question about FEM. So that might be fun to cover in the future as well. So this thing, based on this question, that's what we're doing right now, because this is very important. All right, so now let's backtrack a little bit and call this, let's call this, I guess, pressure example. Right. So let's look at some other stuff, because you might have been playing around with Vellum, and let's say you've been trying to sort of do a whole bunch of like bouncing balls, maybe like just falling toys or whatever, just playing around, making something fun. So let's say we want to do, let's do a balloon again, let's do a sphere again. Polygon. Right, give it a couple of subdivisions. Balloon. Right, configure balloon. So we have this stuff. And let's say we actually want more than one ball. So you might say, all right, let's do grid. Let's copy 2 points. Let's copy these spheres to it, and then create these constraints. By the way, if you hold Control, you can drag stuff that's below it. If you hold Shift, you can drag the stuff that's above it. So if you didn't know that, now you do. All right. So now we're going to create constraints from this. You see a whole bunch of constraints. Let's do a grid for them to fall on. All right, Vellum solver. Let's plug it in. All right. So we're going to have a couple of balloons falling down. You see it's not as fast as a single one. Boom, but I mean, it's working. All right, now let's say we make this a little bit more extreme. All right, let's move this up. Let's do 5. Let's have a whole bunch of spheres. And now you can see this is gonna, I mean, it's still relatively fast, because remember, this is running on a 4090. So it's, but like if you're running anything less, it will probably already start to get pretty slow. Because these are all individual pieces of geometry, all individual constraints, and it's not the fastest, but I'm actually surprised how fast this still relatively is. Kind of looks cool. Boom. Yeah, but there's also other ways that you can do this. So instead of sort of creating all these constraints like we do here, we have all these constraints, all this geometry. We can actually also do is, let me just grab my sort of Vellum setup from the DOP network so I don't have to do it all over again. All right, put it down. All right, so we're gonna have this thing, and we're gonna need to put a static geometry in there as well. Or we can just do, let's do a ground plane. It's gonna be easier. Right. Move it down a little bit. All right. All right, and that's the gravity force. It's actually interesting, by the way, something that I never noticed before, and I'm not sure if it's a common issue, but with the falling papers, it's called leaves because I first had leaves. There's actually an interesting issue with the gravity force. And I'm thinking, because I've noticed the issue before and I never discovered what it was from. As you can see here, I'm not using a gravity force. Let me show you the issue. Sort of sidetracking a little bit here, but in case you ever, so this is all sort of falling completely fine. You can see it's falling, looking good, nothing going on, all fine. Let's say if I remove this pop force with a gravity force, it was actually interesting, and I've run into the issue before, and I never knew that it was caused by using regular forces. Let me press play. Let's see if it might not be there, but some will sort of stick in the air. Let's see if it actually happens this time around. I might just look. All right, yeah, I turned down the time here, so I think maybe it's happening over there. All right, now you're not gonna see it. Anyway, there was actually a thing where some were sort of sticking in the air, which was interesting. So they would essentially just get stuck in the air, even though they were not colliding on anything. I've run into that before when emitting a whole bunch of leaves for a project that I ran into before, and I had that today as well, and it was fixed by not using gravity but using pop force. So if you ever run into that, then now you know. All right, let's continue. Let's continue with the actual sort of example. So here we have this thing. So we have gravity, and it's gonna fall down. Beautiful. All right, so same example. But what I want to do instead of sort of creating constraints like this is I want to create constraints like this. So just on the one sphere, I'll call it geo, and call the other one constraint. So it's disconnected for now. Let me just do my dual view again. Right. So if you can, by the way, bookmark views with Ctrl+1 and Ctrl+2, and you can immediately sort of jump to it with pressing Q2 without control or 1 without control on your keyboard. So that's kind of cool. If you didn't know that. All right. So I'm going to put I'm going to put the source like this, and I'm going to put source like this. And instead of sort of setting it like this, I'm going to say it to instance on points, and I'm going to be giving it some points. Let's actually have a look at this, and let's not copy that. Let's actually copy a point. Let's make one point. We're going to have a couple of points here. Call this points. I'm going to drag these in the points, and then we're going to have a look at in our solver. You can see now I actually have this stuff. Keep in mind, this is gonna work every frame, so we need to say right $f below, or let's say $f equals 1. So if we do that, it will only source it on frame 1, and then after that it will not do anything. Let's press play. This will be a little bit faster because right now what it's doing, it's sort of instancing all these constraints in geometry. So it only needs to keep information from one of the pieces of constraints in memory. And I mean, it's still relatively slow because we're dealing with a lot of geometry. But you can see this is quite cool because we can start using this to also source stuff into our Vellum simulation. And then we can start combining it with other things. So yeah, you can sort of you can instance stuff on this like this. You can also, by the way, you can give this a stream name if you want. So by default, it's called Vellum source. So depending on that, but you can give it another name if you want. And here are the bindings, stuff like that. Yeah, so that's how you can sort of set up an instance for this. You can see now, right now, it just does it once. But let's say I don't do it like that. Let's say I scatter some points, scatter maybe 2 points. Let's say I want to change the seed every frame. If you type $F, sort of, if you type $F here, it's going to change the seed every frame. So because here it's going to be sort of, a seed is going to be 1, going to be 2, going to be 3, going to be 4, etc. Let's have a look at what this is going to be doing. All right, and we need to just keep the activation here to 1. So let's actually delete this. Sometimes there's issues where it just doesn't delete the channel. All right, gives it a 1. All right, and now, all right, let's put it to 1 because it's going to immediately get quite slow. So you can see if we do this, boop, 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 we're actually sort of sourcing these things into the simulation. It's starting to look pretty cool. You can see there's some issues, like stuff is starting to be sort of sourced into one another, which might be something that you don't want, which again, we're going to be covering in our example. So you can see here, that's sort of not happening. They're not being sourced into one another. Yeah, you can see, you can already have a lot of fun just playing around with like stuff like this, like boinchy, 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 boinchy. Good, clean fun. Really need to make sure that I sort of sit up straight. Like my upper back is hurting a little bit. Yeah, I think it's like wrong posture. So I need to make sure that I actually sit up, but it's easy to just start slouching. So if you see me slouch, let me know in the comments that I should not slouch. Right, so I'm gonna try to sit up straight now. But yeah, we have we have this going on. We can start building on this. All right, so let's say that we want to we want to have these spawn in, like I have in my example. Again, we have to spawn in and then grow. Oh, we already know sort of how to do the grow thing, so we can try that out. Let's start maybe with like a lot smaller sphere. I'm just gonna spawn very small spheres here. So this might actually be a good point, like a good spot to sort of pause the video, because you should know how to do this. This might, so to pause the video, try this yourself. Come back if you don't know how to do it. I'm gonna explain it now, so I'll give you a couple seconds. 3, 2, 1. All right, let's go into the explanation. All right, let's do GeoWrangle. I'm gonna attach it here. I'm gonna set it to primitives. Again, we want to run on the constraints. And we want to run it over constraint geometry. And we want to say, all right, we have this rest length, this rest length thing. All right, we want to do if maybe, all right, if rest length is below open bracket, close bracket, and do a second bracket because we're already need to close the first statement, right? First statement needs a closing bracket, and this statement needs a closing bracket. Rest length, original rest length, times, let's do times 100 maybe. And then we're gonna open and close, and we want to type some stuff in between here. And then we're gonna say, all right, at rest length times equals, right. And we want to run it just on the pressure constraint. And all right, now it's giving me an issue with the pressure group because I don't have, right, like I don't have it enabled yet. Call it pressure. Important. All right. And then I can turn this down, I guess. Right. So now we do have a pressure constraint, and now this should work. And I do want to increase it a little bit faster. Right, are they increasing? I'm gonna increase this threshold a little bit. They can actually increase a little bit more. All right, let's try without the if statement. For some reason it's erroring, or it's not erroring, but it's not doing anything. So let's just have a look at if this is actually working. Want to see where the issue is coming from. Do I have a typo? Rest length. All right, there we go. Okay, so here you see one thing playing in. I had this before. Let me undo this as well. Okay. So we're starting off really small and then sort of start to exponentially increment. Maybe we want to, because in the beginning they're quite small. So maybe we also, instead of just multiplying them, maybe we also want to, there's a couple of things I want to try. So we can also, instead of multiplying, we can also add something to it. So we can say plus equals, let's say in the beginning, we just maybe want to add 1 to the original wrestling. Like maybe add 10. Right? Let's increase this. Oh, that's too fast. Right. Right. So now we're adding a little bit to it instead of multiplying. Again, if you multiply, it's going to get exponential. With this, it's just going to do linear growth. You can see them sort of really fast, sort of inflating. Here's where some options on the pressure constraint come in. Because remember, all of these constraints have sort of parameters on them, right? Like our pressure constraint. Let's have a look at our pressure constraint by sort of deleting and keeping some of this stuff. Pressure, not selected. Let's look at the first input. So our pressure constraint has a bunch of attributes as well. So it also has a stiffness attribute, which is the one here. So again, depending on how stiff it is, will depend on how much it's allowed sort of to stretch. If it's much stiffer, it's gonna essentially not be allowed to sort of quickly inflate. Let's try what happens if we just maybe put this to 1000. It's already a lot better. As you can see now, it's more of a nice sort of bloop, bloop. Right, we can try maybe doubling it. Right. Already looking a lot better. We still have this issue, of course, here where they're sort of spawning inside each other. So we're gonna need to do a little bit some more advanced stuff in order to make that work. All right, so we're gonna do something interesting. We're gonna use another slope solver, but in a sort of a hacky way. And this might get a little bit confusing. So don't worry, it's not you. If you're a beginner, this might get confusing, but this is an issue that I wanna go over. And again, this is something that you're gonna run into. So I might as well cover it and then you know where to come back to if at some point you run into this when you're dealing with this in production, because this might be a very typical scenario. All right, let's make a solver. All right, slope solver, slope solver. All right, and we're not gonna put anything in between here. So with this slope solver, again, if you wanna know a lot about slope solvers, watch my course around slope solvers. I'll put a link in the description. It's all about slope solvers. You learn how to use them to your heart's desire to make your own custom solvers, actually. We're not going to put anything in between here. So how slope solvers work is this brings in sort of the geometry. It's going to do something and then output something here. So we can use all kinds of cool slope tools. We can use all of our trusty slope arsenal. That's why I love slope solvers, because I just love working in slopes, because slopes are easy to work in. And you can do stuff in between here. If you don't put anything in between here, it's not really going to do anything. It's going to add a little bit of overhead and speed, but you see it's not the biggest. It's very mild. All right, so what I want to do here is instead of sourcing here, what I want to do is I want to source from my slope solver. You might be like, oh crap, this is gonna get difficult. It's not too bad. Right, so what I want to do is I want to just paste this in our slope solver. Just copy this out path, just Control C, and let's paste this into our Vellum source. All right, we're gonna source from there. We can also just do is maybe to let's call this, because to get a better path, we could also just call this our let's call this source PT, and we can also just do /source PT /PTS. That way, doesn't matter where you sort of put it in your network, this will always work. If we press play, you can see it's not nothing changed. I guess the way that it looks now is a little bit different, but because it's the way that I guess the points are scattered, it might be a little bit different. But yeah, what I want to do is now I want to actually look at our sort of dot geometry that we have here. I want to say, all right, if one of these points is inside one of these things, remove it. So then they don't get sourced. So first, what do we want to do? All right, I want to first maybe, if there's use a peak swap. So peak swap, essentially all we'll do is just sort of peak out the normal. So we can sort of inflate our thing a little bit. All right, inflate it. Rip. Right, now what I want to do is I want to do a VDB from polygons. So this will create a sort of, if you don't know about VDBs, let me do a very brief sort of overview of what VDBs are. Let me just do it somewhere else. Because again, like I want to make this introductory as beginner friendly as possible, even though we're already doing something more complicated. But these are very fundamental things to using Houdini. So, right, so let's do a sphere. Let's make it a VDB. So VDB is it's a volume. There's two different types of VDBs. You have a distance VDB, which is this, and you have a fog VDB. And for some reason, the viewport is bugging again because it's showing my geometry instead of my VOG volumes. Let me make a new viewer. Right, there we go. Let's make my viewport dark. Right. Right. Okay, so we have this thing here. So essentially how it is, let's do a volume slice. And with the volume slice, we can have a look at these values. Essentially, let me increase the resolution a little bit. So if you make this smaller, resolution is going to increase. Essentially, a VOG VDB is essentially going to be, all right, on the inside, it's going to be 1. On the outside, it's going to be 0. So we just have a density. And these things are, like if you've done a smoke simulation, that's what this is. But they're great for saying, all right, for masking stuff, because this is a hard sort of, right, inside, outside. A distance VDB is going to be different. There's going to be like a band. We can have a look at these values if we want. So you can see let me visualize these in a viewport. If you press D, you can open up this thing. You can type. I want to, let's call this density as well. Right. I want to visualize density in a viewport. All right. So here you can see sort of a bending region, right? So over here you can see sort of increase inside. So on the actual surface of this thing is going to be 0. And going out of it is going to increase in value. And on the inside it's going to decrease in value. You can see it caps out at -0.6 is because VDBs are sparse. So they you have these band voxels here. If we increase the band voxels, essentially it compresses. Like the stuff on the completely inside is like, we don't need it, we can throw it away. If you increase these bands, you can see we get a little bit more information around it. So now you can see where you get increasingly negative values and then increasingly positive values on our volume. And these are super useful to be able to do things in Houdini, because we can use this to, for example, say, right, because here we have, let's run through our simulation a couple of frames. By the way, let's do this example first over here. It's going to be easier to see if we just do it over here. All right, so let's make it the distance VDB. Let's just call it surface, because normally it's the default name. All right, and let's do like a grid. Let's scatter some points on it. Oh no, not quick cell scanned. All right, scatter some points on it. Increase the points. All right, we got a bunch of points. Let's do an attribute wrangle. Again, we're gonna learn some more vex. Amazing. And again, don't have to be scared of vex. We're gonna I like this is how I learned vex, by just using just doing these just small examples that you just learn throughout just throughout working, and then you just implement it. All right. So we're going to do something called a volume sample. Right. So what I'm going to do if you're setting attributes in Vex, there's two ways to do it. If you type f at and then give it a name. So for example, f at cheese equals 1. You You see, you're gonna attribute them all my points called one, like called cheese, and it's 1. So this is just a global attribute. It's being contained on the points, and it will carry through to other nodes. So if I make another node here, you can see also called cheese. If you type float cheese equals 1, essentially this attribute is still here. It's just not being written to the points. So not taking up any space on the points, but it's still here. So we can still use it. So if you don't, and of course every attribute you're going to write on here is going to take up data. It's going to take up size. Like we can demo that if we want. Because like here, this is going to be 1.15 megabytes, and now it's 1.16. So it takes a little bit of data. Well, if we do float cheese equals 1, it's just the same because it doesn't write anything to it. And again, we can, so just to preface, so we want to do something called a volume sample, which will sample these values on this thing here, and then say, all right, if the value is going to be negative, apparently it's going to be inside of this sphere, right? So we can delete it. That's what we're going to be doing, right? So we're going to first create a container variable. So float, give it a name, maybe sample is easy, and right, equals. And we're going to type volume sample, open bracket. And again, you can we can hover over this, press F1, and then it should open the help. And all right, there we go. All right, so this is going to say what does it want? It wants the geometry, so it's going to be first input. Again, start with 0. So first input 0 is first input, 1 is the second input. Right. Primitive number or name. So we want to just give it a name, surface, because that's what this was called over here, surface. And then the position, vector position. Sometimes it might say string, and then you'd put it between sort of these things, sort of these sticks. But again, we just want position, so we're going to say P. If you want to be accurate, you should type V at P, so vector, because it's a vector. Right. Now, this thing contains our sample. You can try this out if we type F at sample now, F at sample, and we're going to write this out to say sample. So this is going to now write this value to this. Okay, we can see 0, 0, 0, 0, 0. And, oh yeah, that's because... Yeah, I was explaining with the input 1. We need the second input. Yeah, all right. So now you can see we get this sample value, right? So you can see it goes from negative to positive. And of course, the positive values are going to be the ones that sort of are going to be outside of the sphere, and the negative values are going to be the one inside the sphere. Easy peasy. Right. So we can say, instead of doing this, we can do another if statement. So if sample below 0, we're going to do another thing called we can do two things. We can group them, or we can remove them all together. If you type group underscore and then give it a name, cheese, for example, equals 1, it's going to create a group called cheese. So again, can have my group here, points, need not selected. You can see now I have my points here. I can also just remove them here. If I say, right, remove point from the first input, so 0 first input, and then I want to remove the point number. You can see this will do the same. And we can also create a slider for this if we want. So let's create another placeholder. Call this range or something like that. Or just call it D or whatever. I just letters can be just add letters. Usually it's quite easy. Right. So if you do want to do CHF, create channel float, very easy. And give it a name between either these sticks or these sticks, and then call it give it a name, remove backtick, and then close these colons. Then if you press this slider icon here, you're going to create a slider, and then we, instead of sort of sample between 0, we can say sample below D, and we can say we can actually get a. So after a while it completely disappears. It's because this, like, we have these bending, right? We have the bending that we contend with, and we can also make it negative. But yeah, this is the way you can sort of. I'll put a note, or I put a thing around this. You can easy to find. Again, you can download these files on Patreon, and I will also put this stuff on Gumroad later. I'm not sure what to do with Gumroad, if I should just put them by week or if I should just make an increasing price, like the more stuff is in there. I don't know. Let me know what you think would be good for Gumroad. Yeah, just call it the volume sample example. Right. All right. All right. So we can grab this. Just grab this code or just grab this entire thing. We can go in here. Go in our stop solver thing here. Just paste this. And surface. Right. So below 0. So now essentially it's gonna first, let's first just run a couple frames through this. All right, so what it's gonna do, it's gonna peek the geometry here. It's gonna make a VDB from it. Then it's gonna do volume sample for, so there's points being scattered. If I can increase it. So if then it's gonna, it's going to remove the points on the, and why is that not showing? Oh yeah, now it's, oh yeah, right. Wait, I'm gonna, yeah, it's because it was recooking because I have all of these points. So it's just sourcing a lot of this stuff, right? So I'm just gonna show it like this. So if I, let's say on this one, I'm gonna have a lot of points and it's gonna be, if they're gonna be inside, it's gonna be removed. Well, we're just gonna do that with our 1 point. I'm gonna drag that in. Maybe you can increase the peak a little bit more. So we just have a little bit more to work with. Right, and now this should not scatter points inside of other things. Easy peasy. See, they're being pushed off to the side a little bit because some are inflating and I'm pushing the other ones away, of course, but so yeah, pretty cool. That's essentially just all I've did for the balloon example. Implementation is slightly different, and with the addition also that I'm colliding with a box, so they're being scattered inside the box, and there's a font, so they sort of squeeze up to the side of the box. You can see here, they have a lot more geometry going on, of course. And there's a couple of extra nodes. Like I added some drag. I'm disabling this thing to not increase them after frame 45 instead of, like I could have done this in a wrangle, but you can also use enable solver like this. Little bit different, but aside from that, it's the same. Like if you want to just recreate the exact example, you can have a look at this file. It's going to be on Patreon. Again, it's also the file has the render setup for it. So you're able to render this. Oh yeah, I should go over here. All right, because, all right, let's go here. All right. Yeah, so you'll be able to have a look at this. All right, so let's go to our other example, which are these leaves. Or not leaves. I call them leaves, but they started out as leaves, and I thought like pieces of paper would be cooler. Because we're educating and paper and whatever. I don't know. It just was cool. There's another thing here. So the pieces of paper that emit have different scales. Right? They're not all the same scale. Which brings some extra issues that, like, if you might already know what the issue is going to be. If you don't, then yeah, whatever. Like if you think you know what the issue is, leave it in the comments, and then maybe you're right, maybe you're not right. Let's make an example for this, and I can show you kind of what the issue is here. This is going to be a little bit more tricky as well. All right, I'll call this balloon example. Let's call this paper. All right, here we go. All right, let's do, maybe you can grab some of the stuff from our bubble setup, or from our other example to make it a little bit easier to set up. Let's see, and you know what, let's do another one. All right, grid, scatter a couple of points. You don't want to scatter too much because it's going to emit every frame. Let's do $F. I'm gonna change every frame. Let's say, all right, I'm gonna say PTS. I'm gonna emit a piece of paper. So we're gonna do a little grid, 0.5 by, maybe do, right, something like that. Can add like a UV project on it. So we have a UV on it, and then call this cloth, figure cloth. Right. Geo and con. Oh. All right, we're gonna do another dop network. Vellum solver. Vellum. I know there's a lot of reiterating, but again, you're learning, so that's good. Source. Adding it here. Right. I'm gonna put the geo in. I'm gonna put the constraints in. And we want to instance on points. I'm gonna put in the points. I'm gonna put in, let's do our pop force instead of regular gravity. Because again, I had some issues with that, which was interesting. I mean, it should work, but there was some weird stuff going on. All right, and we have stuff going on, just falling. Again, maybe do a different one that has like a little bit of noise. And there's where one thing comes in that we did discuss last week, where we haven't seen a lot of examples for it. Here we can change this drag. So actually tangent drag here makes quite a bit of difference, sort of the way that they're going to be sort of falling. And we probably also want to change the normal drag and probably want to decrease the amount of gravity because this is too much. Just do regular gravity. All right. Let's do this one. Do a little bit more noise. You can see if you really increase this drag here, you can see they're going to sort of spin a lot more. Maybe something like 50-50 or something. Again, just play around with it. You can add multiple noises. Maybe like one very large scale and then one that's a little bit smaller. And so maybe something like this. This is, by the way, also, as you can see, if you have ever seen the meme, the money printer go blue, I actually made that. Like, this is the original. It's on my channel. Not everybody knows that, but this is this is how I did the money here coming out of the money printer. I've made a viral meme. Yay! All right, but it's my most viewed video. It's kind of sad, but I guess this reaches a larger audience than my very niche Houdini tutorial. Anyway, so yeah, we have this, but let's turn this down a little bit for now. All right, so let's talk about this issue when emitting different scales. So let's first let's do attribute randomize, which allows you to randomize an attribute. Let's say we want to randomize pscale between 0.1 and 1. All right, let's have a look at what's going to happen. Maybe turn off the gravity. Maybe turn off all of the forces for now so you can have a look at it. Right. So what you can see here is they get emitted and they immediately sort of they grow, which looks cool. I mean, don't get me wrong, it looks cool, but they end up having the same size, which is because when we changed the pscale, so we changed the way there being instance on this, but the constraints, like the rest length of the constraints, is still the same. I personally think there should be a way for this to sort of do this automatically, because I think it would make a lot more sense if this Vellum handles this under the hood if you want. But as of right now, it doesn't. But we can make that work, which is what we're going to be doing. So we can leave a look if we play through this. By default, it's not even gonna pick up on our pscale. If we look at this thing and then, well, we can see it does pick up on some pscale. I think this is the pscale that this creates. So we probably should also give it second name. So this gives some pscale that's being instanced on it. And then maybe we want to give another pscale name as well. Let me call it at my scale equals pscale. Right, so we're gonna have a second attribute, and we're gonna press scroll through this. Like, this is not gonna pick up on my scale by default, because we need to tell this to pick up on it in the instance attribute. And you can see we're actually picking up on the attribute. Right, now what we need to do is we need to create a SOP solver again. Constraint, but we want to say it to be SOP solver constraint geometry. So this is set up a little bit different. It's set to have additional data attached, so it runs on both the geometry. You have the geometry and it has a constraint geometry. And if you look in here, it actually has a compile block. Again, a little bit more advanced. What compile block does is everything that's in between here is multi-threaded. So this will run on all the cores. Like, a lot of SOP nodes are not multi-threaded, and you can actually you can make stuff in SOPs also multi-thread yourself with a compile block. Compile block, all right. Compile block, there we go. If you, for example, have a for each loop like that, if you've not used it, for each loop essentially runs over. I can show you. Let me just show you. Like, this video is getting long enough as it is, and might as well make it even longer. All right. I should really make my lessons maybe smaller. All right. Load for next week. That next week's video will probably be a little bit not as long. All right. Let's do. All right. So here we have some spheres. If we put this in for each loop, just without the compile block here, see, if we do it like this, it's gonna run over each connected piece. If you check here, you can check just one iteration. You can see, you can check the iterations like this. But the compile block, for each loop doesn't multi-thread, so we'll just run on single core. If you check multi-thread when compiled, it will do one iteration on each of your cores, and it will be a lot faster. But not all of your SOP nodes that you have here are able to multi-thread. Anyway, so a lot of information there, but this thing just creates a compile block as well, so it can have two different outputs. Meaning, because it's a compile block, you cannot use all of your SOP nodes in here. The benefit here, though, is that we have both our regular geometry and we have our constraint geometry. What we can actually do is we can grab an attribute and we're going to transfer an attribute from our points to our constraints. So we can say, all right, points, I want to grab my where is it? My scale. I'm going to transfer it. So this is going to copy. Now, so if we have a look at here, you can see, all right, these are our constraints. And now our constraints are going to have the my scale attribute, which they didn't have before. Well, I mean, now it does, because this will just run while I'm making edits, but it didn't have it before. I can show you if I just do it like this. All right, let's run through a couple of things. All right, doesn't have it. Now it does have it. These are point attributes, again, are our points, so we need to promote this. Point to primitive, my scale. And so now the my scale is gonna be on our constraints, primitives, my scale. All right, here we go. And now what we can do is we can sort of increase the constraint or increase or decrease the constraint size, depending, like, we can scale it by our pscale. Thing is, we only want to do this once. So we need to initialize an attribute that sort of says, all right, if this attribute exists, don't do it again. So I guess I add my cheese or whatever. Just give it a name. I don't care. So I add stands for it was going to be an integer equals 1. Right. I'm going to put that at the end. We're going to say if my cheese, all right, well, I add my cheese equals 1. Does not equal 1, because we don't want to do it if it's 1. Then we're going to execute this block here. We're going to say, all right, at rest length times equals at my scale, right? So essentially something coming, we need to run this on primitives, by the way. So something coming in here, you can already see it do something. Something coming in here is not going to have the my cheese attribute. So my cheese is going to be 0. All right, so my cheese is 0. Then it's going to multiply the rest length. So the length of our constraints. I'm going to multiply them by our my scale attribute, which is again the same as our pscale attribute. And then my attribute my cheese is set to 1 after this completes. So the next frame, my cheese will be 1. So it will not execute this. So we'll only do 1. If we didn't do this, it will just keep shrinking it. Right, but let's have a look. And you can see now they actually stay the same size. Now we can run the rest of our stuff and it'll all look cool. Probably the size is going to be a little bit, probably need to a little bit bigger, but this will work just fine. And again, these are actually already a little bit more advanced techniques. There's a lot of people that probably don't know about this. So if you're watching this as a beginner, these are things that you're gonna run into and you're gonna normally spend a lot of time to figure out, and now you already know how to deal with this. Yeah, so now you have stuff falling down, and then it looks pretty cool. And yeah, there you go. All right, so I think those are all the examples for this week. Like again, you can look at the thing in here as well, way that was rendered. So you can look through camera here. It's rendered in XPU and just some simple materials, some simple settings. So if you download the file, like all of this stuff will be in there. So yeah, like everything will be in there, including the rendering setup. You can look through it. And again, if you download the file on Patreon, it really helps me out with being able to make videos, because it takes quite a lot of time to do. Even though like I'm doing it once a week now, but still I've like spend some time making the examples and preparing everything. But yeah, all right, here we go. You can see here's our paper. As you can see, I scaled it up a little bit. It's a square because I wanted to match the size of the I wanted to match the size of the text, so I just matched that in comp. All right. Yeah, that's it for week 2. Again, if you want to help out the channel and download these files, you can get these files on Patreon. These will be in the beer tier. Last week's one was in the lower tier, but these are a little bit more advanced. Well, not necessarily more, a little bit more expansive, and there's also just rendering stuff. So I'm gonna put them in a little bit higher tier. So if you want to help out the channel, would really appreciate it. All right, so thanks for watching. Hopefully it was interesting. Hopefully you learned a lot. I know some stuff was maybe a little bit on the more difficult side, but still, hopefully it was still manageable. Hopefully I talked you through all of the sort of the VEX and subsolvers and stuff like that in a way that was understandable, even if you're a beginner. I'm not sure what I'm going to be doing next week, so let me like if you have suggestions. Like I'm just going to go through the suggestions to sort of build this weekly series up. So if you have suggestions for next week, or like I'm not going to do a strict release schedule that I'm going to do it on the same day. Like it might shift a couple of days here and there. I'm going to do it around every week, but depends on how the preparation goes and how other work that I need to do is going to go. But just so you know. But like if you have suggestions for future videos, topics that you want covered, let me know. If you want to help out the channel and get access to the source files, they will be in the description. The course about building custom subsolvers, like custom solvers in Houdini, which is a paid course. There's introductory stuff on my channel. Is going to be in the description as well. So you can check the playlist and you can buy the course. And that's really going to go really deep into these custom solvers, VEX, and just very interesting stuff. So if you're interested in any of that, you can get that in the description. I'll put a discount code, I guess, for Gimroad. I'll put a discount code on this one. So if you find it through this, then you can get it cheaper. And yeah, hopefully I'll see you next week. So let me know if you have suggestions, and until next time. Peace.